In this module, we're going to be talking about virtual networking, specifically how virtual machines are going to connect and communicate with other devices on the network. Now, those devices can range from other virtual machines to physical servers, appliances, or even other networking devices that are available on the physical network. So brace yourselves for a really cool module. Alright, let's get started. But we're going to start off with a general overview of virtual networking. So what is virtual networking and why do we need it? Virtual networking, in its purest form, is simply the building block or the cornerstone of an IP network that's built primarily for virtual machines. Now, this virtual network, virtual IP network that we're building is going to help connect those virtual machines to the physical network. So the same way physical machines and physical devices require a physical network in order for them to communicate with one another, virtual machines also require a virtual network in order for virtual machines to communicate with one another, but also to integrate this virtual environment with the physical environment and allow for a seamless connectivity of virtual machines or virtual devices with physical machines and physical devices. Now, I've always said that whenever you think about virtual machines, you got to think they have the same components, the same requirements as physical machines. So a physical machine requires a physical NIC card, a virtual machine is going to require a virtual NIC card. If a physical machine requires a switch, a physical switch to connect to in order to get access and have communication with other devices, then a virtual machine is going to require a virtual switch to connect to and get access to other virtual machines and other devices. A virtual environment mimics a physical environment, except instead of having physical hardware, you have virtual hardware. So let's bring up a whiteboard here and illustrate a little more how this works. In the traditional sense of networking, each device required a NIC. This NIC allowed the device, whether it is a server, an appliance, a router, a printer, whatever it is, it allowed this device to communicate with the rest of the devices and appliances that are on the network. Now, with the introduction of virtualization and VMware, you have one big host, which is the physical device, and then you have several virtual machines running on this physical host. Now, in the traditional sense, you would need a NIC card for every virtual machine to allow connectivity to the rest of the network. So what do? It doesn't make sense to add 20 or 30 NIC cards in a host to give connectivity to all these virtual machines. And this is where the concept of a virtual switch comes into play. A virtual switch mimics a physical switch, except it's software based, as you may know, and it will have ports on it. And these ports can be added or deleted. You can have 24 ports, 51 ports, 52 ports on a virtual switch. Now, the idea here is to connect one or more NIC cards, physical NIC cards, to this virtual switch. So this virtual switch is serviced by one or more physical NIC cards. At this point, what we do is we connect these virtual machines to the different ports that are available on this virtual switch, and as such, we give them connectivity to the outside world or to the network. Now, this is just a very basic idea. That gets more complex and it's more interesting, and we're going to get into the different scenarios and different types of scenarios that we can tackle here. But I just wanted to give you a quick breakdown of how things work in order for us to be able to make more sense out of the next slide that I'm going to bring up here. Alright, so let's move on with our presentation here. ESX Server is going to perform a discovery of all the available physical NIC cards that are installed on this host. And as you can see in this figure, and we're going to log into the VI client in just a second here and show you how this looks like in a live server. But as you can see in this figure, under the configuration tab, if you click on network adapters, you're going to see a list of all the physical adapters that are available, and if they have an IP address that's assigned to them, that's going to be displayed too. If they're part of a trunk, you're going to see a subset of IP addresses that this NIC card can see or has access to. Alright, so once you've logged into the VI client, if you click on the configuration tab here, as I mentioned to you earlier, and you click on the network adapters link on the left, you're going to see a list of all the NIC cards that are installed. You're going to be able to tell if they're connected. You're going to be able to tell the duplex speed that they're connecting at. So for example, here you can see that I'm connecting at a gig. some of these interfaces are down, which means a cable could be unplugged. You can see how they're configured, if they're configured for auto negotiate, if they're hard coded to 100 meg or a gig, for example. If they're associated with any virtual switches, you'd be able to see it over here, and then the IP addresses that they can see, or the subnets that they have access to. So from here, let's move on to virtual switches. Now, virtual switches are going to be under the networking tab, and we'll come back to virtual switches here in just a second. Let's go back to the presentation. Alright, so virtual switches are logical objects that reside in the VM kernel of each ESX server host. What this basically means is that virtual switches are made up of software that live inside the VM kernel. Now, the same way a physical NIC that's connected to a physical switch has a unique MAC address that identifies it on the network, a virtual NIC connected to a virtual machine is also going to have a unique MAC address that identifies it on the network. Now, with virtual switches, you can also bound one or more physical network adapter cards to each one of these virtual switches. Virtual switches can also contain one or more connection types, otherwise known as port groups. Port groups, or connection types, define the type of communication expected through the virtual switch. We're going to get into this in more detail a little later on in a few slides down. Virtual switches also operate at layer 2 and can provide VLAN tagging, security, checksums, and segmentation of load units. Now let's take a look at some of the similarities that exist between physical switches and virtual switches. Virtual switches are similar to physical switches in that they both maintain MAC address tables, they both look up each frame's destination MAC upon arrival, they both forward frames to one or more ports, and they both avoid unnecessary deliveries. Now, some of the differences that exist between physical switches and virtual switches: virtual switches cannot be connected to other virtual switches, whereas physical switches can be connected to other physical switches. Virtual switches do not require spanning tree protocol. They also prevent loops in the switching configuration by using virtual switch isolation. Forwarding table is unique to each virtual switch. Now, there are three types of virtual switches that exist. There's the internal only virtual switch, which is sort of an isolated virtual switch. This virtual switch has no physical NIC bound to it, which means the virtual machines that are connected to this virtual switch have no way of communicating with the rest of the network. Now, this would be ideal if you're trying to set up some kind of a test development where you wanted to isolate an application and you wanted to build an environment that mimics your existing environment, but you didn't want to have any kind of conflict via either by using the same names or by using the same IP addresses, or even if you're doing an Active Directory domain and you didn't want SID conflicts or having different domain controllers that are playing the same roles. You could create your entire environment inside or access through this virtual switch that's isolated from everything else. The only communication that happens with an internal only virtual switch is between virtual machines that are connected to this internal only virtual switch. Now, the second type of virtual switch that exists is a single adapter virtual switch. This basically means that the virtual switch is bound to a single physical adapter, and this physical adapter is this virtual switch's way of communicating with the rest of the network. Now, the third type is NIC teaming, whereby you bound two or more physical adapters to a virtual switch. This provides for load balancing and bandwidth aggregation for communication with resources on the physical network. Alright, so examining what we have currently configured on this ESX host, you're going to quickly notice that we have one virtual switch right now that is considered a single adapter virtual switch because it has one physical adapter bound to it. And I'm going to get into this a little more details, but this is what I mean by multiple port groups and multiple types. So this virtual switch has two port groups. A port group for service console, which dictates the type of communication that's going through this virtual switch, and then you have a port group for virtual machines, which means the type of communication that this particular port group is going to be supporting is virtual machine communication. Alright, so now let's create a virtual switch that can be considered an internal only virtual switch. So the first thing that we're going to do here is we're going to click on Add Networking. And then let's create a port group type of virtual machine for this example. And if we're going to create an internal only virtual switch, this means we're not going to be associating any physical NICs with this virtual switch. So I'm going to uncheck this. We're going to click next, and let's give this a name of internal. I'll click on next here and finish. And this is what we mean by an internal only virtual switch. Now as you add virtual machines to this virtual switch, the only communication that these virtual machines are going to have is between each other. Only virtual machines on this virtual switch are going to be able to communicate. Now as far as a NIC team virtual switch is considered, we're going to click on add networking again. Let's choose virtual machines again. And as soon as you select one, actually two or more physical NIC cards, then you're going to end up with a NIC team. We're going to click on next here, and let's call this virtual switch the NIC team virtual switch. If I can type and not put a capital E, that'd be great. I'll click on next, finish, and voila. Now in the event that one of these NIC cards is going to go down, the other one is going to pick up and continue to service the virtual machines that are configured on this virtual switch in a seamless mode. The virtual machines aren't going to be affected whether or not one of these two physical NIC cards goes down. And you also have bandwidth aggregation. This is just a fantastic solution here. Just imagine if you're trying to do this in a physical environment, how long it would take you. It's taking me 5 seconds to create, virtual switches and have different configurations attached to them. So we've been talking about port groups. So what are port groups? How many port group types are available? To do that, let's bring up the wizard here again. These are the type of port groups that you can configure on a virtual switch. Again, you can have virtual machine port group, which means virtual machines are going to be communicating through this port group. It's typically what you would assign for virtual machines. Then you have the VM kernel port group, which means you're going to be configuring either vMotion, iSCSI, NAS, or NFS. And then you have the service console port group, which means that you're going to be using this port group for service console and the management of ESX. Now as you can see here in the figure before here, you can assign multiple port groups to the same virtual switch. Let me show you. If we click on properties here, you're going to notice that there's the VM network, there's service console. If I click on add, the wizard comes up and I can add more port groups as I need to. So let's cancel out of here. Now it goes without saying that the service console connection type here is used for communicating back and forth between the service console. In other words, it's used for service console communication. Now the connection type for service console requires that you configure it with an IP address. Let's go in here into properties for a second. Let me show you how this works exactly. So we're going to click on service console here, and we're going to click on edit. Now it's going to come up with a warning that if I need to make any changes, it is recommended that you create another service console and not modify this one, etc., etc. We're just demoing here, so I'm going to continue to modify this, and you can see the IP address that's assigned to it, the subnet mask, default gateway. You can click on edit here, make some modifications. We'll get into how you can change IP addresses and all that stuff a little later on as we move on with the module. Alright, let's exit out of here real quick. Now let me ask you a question. Now the service console is a very important part of ESX communication. If the service console goes down, you're going to have a hard time communicating with ESX. Alright, so let's talk a little bit about service console redundancy. Now I'm sure you would agree with me that the service console is a very important part of ESX. Without that, communicating with ESX server becomes next to impossible. So I would strongly recommend that you take steps towards making sure that the service console stays up at all times. One of these steps that you can do is to assign multiple physical NICs to the virtual switch that's servicing the service console. Now, one of the cool things here is that typically or traditionally what you would do is you assign an IP address directly to a physical NIC. What we're doing here in this case is we're adding a second NIC to the virtual switch that's supporting the service console. But because the IP address is assigned to the connection type, as I'm going to show you in a second, adding that second physical NIC means that you just created a redundancy. So if one of the physical NICs should go down, the other one will pick up and continue to respond on that IP address. Now that's pretty cool considering how difficult this would be if you're trying to do it in a physical environment. So let's take a look at how this would work. If we click on properties here of the virtual switch that's configured for the service console, click on network adapters up here, and we'll click on add. We're going to add a second NIC that would service this connection type. Let's take this one for example. I'm going to click on next here, finish, and let's get out of here for just 1 second. We'll get back in. Now, as you can see, there are two physical NICs that are servicing this virtual switch at this point. Any one of them goes down, and any device, any virtual device that's connected on this virtual switch will continue to communicate with the rest of the networks in a seamless manner. Now let's take a look here at where the IP is configured. We're going to click on the service console port group, and if we click on edit, we're going to get that message again. We're going to click on continue, and you'll notice that it's on at the connection type level, which means that you can add multiple physical NICs and not have to manually assign an IP address to every one of those physical NICs. Now this is pretty cool. So let's get out of here for a second. But what other options do you have for redundancy at the service console level? What else can you do? Instead of putting all your eggs in one basket and just relying on one virtual switch not going down, you can have multiple virtual switches that have service console connection types, and that way you're not relying on one virtual switch with multiple physical NICs. And the way you would do that is, let's say you wanted to add another service console connection type, and let's add it here. You can come down to properties down here, click on add, and we're going to select service console. We're going to click on next, and service console 2 is automatically going to be given. Now the trick here is now you're going to have to allocate a second IP address to this connection type. But when we're done, what we're going to end up with is we're going to have multiple entries into this ESX host. So let me pause the video, put in some information here, and I'll be right back. Alright, so I've IP'd this connection type, and let's click on finish. So what's going to happen here again is we're going to end up with two entry points into this ESX host. Now what you would do typically is you would keep service console 1, the default service console, you would configure that in DNS so that your ESX host will respond on that port or on that IP address. Now in the event that something should happen to that service console or to that connection type, you always have the backup service console that's connected down here that has another entry point via its IP address. You can always point to the IP address and get access to the service console and ESX that way. Now, what other connection types would you say also require a dedicated IP address, and why? If somebody said VM kernel, then you're absolutely correct. In order for you to configure iSCSI, for example, you're going to have to configure dedicated IP address that connect to the iSCSI SAN. If you're doing NFS or NAS, you're going to have to dedicate an IP address as well. If you're doing vMotion, for example, you're also going to have to dedicate an IP address so that you could tell the vMotion or vMotion's traffic can be separated on its own VLAN or subnet. Now, as we get on with this video, we are going to configure iSCSI, we're going to configure NAS, we're going to configure vMotion, but I just want to give you a quick overview here so that you have an idea of what to expect and what's coming down the line. So if we click on properties and click on add here, let's click on VM kernel real quick, click on next. You're going to notice that if this port was going to be used for vMotion, we would click here, we would fill in the relevant information, click next, and we just created a port group for vMotion. If we were doing iSCSI or NAS, for example, we would leave this off, put the label that we want, put in the right IP address information, and move on. But again, I don't want to get into all of these details at this point. I just wanted to give you guys a real quick overview of how this works. Now let's go back into our presentation here real quick. I want to show you guys the virtual machine port group and some of its requirements. Alright, so the definition of the virtual machine port group is that members of the port group are going to get access to the rest of the physical network via a switch-to-switch connection. So the virtual switch is going to make a connection with the physical switch and pass the traffic from the virtual machines out to the rest of the devices on the network. The physical switch is going to receive the traffic from all the physical devices, pass it to the virtual switch, and pass the traffic that's destined to the specific virtual machines. This is really cool stuff if you think about it. I can't help but remembering the movie The Matrix and the link between the virtual world and the physical world. And you can see the relevance of the communication here. You are mimicking physical devices in virtual, and you're spreading them in virtual. I mean, you're able to have 20, 30 virtual machines connecting to a virtual switch that's then connecting to a physical switch, which spreads out to all the physical devices. It's pretty cool. Now this next slide is really pretty cool as well. It shows you the power of virtualization here. So take a look at this. This green circle, think of this green circle as communication between physical and virtual machines. This is one of the ways that you can configure your virtual switches, is to pass the communication between virtual machines, physical devices, etc., etc. But you can also do, and we talked about this, you can also, with a few configuration settings, create an isolated environment where you have virtual machines operating among themselves, completely isolated from the physical network or from the rest of the virtual machines that are in the production network. Just imagine how much time this is saving you, and how much time this would have taken you to set up an isolation environment if you needed to for a test and development with physical devices. I guarantee it would have taken hours, if not days. Now you can do it in a matter of, I don't know, 20, 30 minutes. You have everything up and running, you're passing it on to the developers, so you're saving a lot of time, you're increasing productivity. That's the power of virtualization. Alright, so now let's shift our attention a little bit and talk about VLANs. So what's a VLAN? In a very brief definition, a VLAN is a logical configuration of a network on switch ports to segment IP traffic. What this basically means is, without VLANs, what ends up happening is all the physical ports on a physical switch end up being part of the same subnet or part of the same network. So without VLANs, there's no way to carve up those ports to say, I want this specific port to connect to this network while that specific port to connect to that network. All the ports are part of the same network. The power of VLAN is it gives you the opportunity to have multiple networks present on the same physical switch based on ports. You can group ports together. Say ports 1 through 5 belong to VLAN 101, which is my server VLAN. Ports 6 through 10 belong to VLAN 102, which is my printer VLAN, for example. So some of the many advantages of using a VLAN is that it allows you to save on hardware. Without VLANs, then every time you wanted to add connectivity to a particular network or subnet, you would have to have another switch. By using VLANs, now you can have one switch and then configure the networks or your subnets on a port-by-port basis. This saves you a lot of money and a lot of time as well. VLANs also allow IP subnets to extend beyond the distance limitations of the physical medium. So typically what happens is a VLAN is present in the configuration of one physical switch, but the VLAN on switch A, for example, doesn't know about VLANs that are available on switch B, and thereby cannot pass traffic to those VLANs. Now this is where advanced VLAN configurations come into place, where you can have certain ports on physical switches that are considered trunk ports. And a trunk port, in essence, is a port that has knowledge of other VLANs that exist on other switches. Now, by having this knowledge, by having those trunk ports, now you've made the VLANs that are available on the other switches accessible to this VLAN. Now it can route traffic to it, it can pass communication across it. Now I'm sure a lot of you are probably asking, why are we talking about VLANs and such advanced networking concepts when we are trying to learn about virtualization? Well, the fact of the matter is, virtual networking is an imperative part of virtualization. And I'm going to give you an example here. Why are VLANs important to virtual networking and virtual switches in particular? Well, without VLAN tagging, without support for VLAN tagging inside virtual switches, you're going to end up having to dedicate a physical NIC to every network or subnet that you're trying to give your virtual machines connectivity to. So if your environment looks like a lot of the ones that I've seen, whereby you have your servers in VLAN 101, for example, and then you have your terminal servers in VLAN 102, and your file and print servers in VLAN 103, and your Novell servers in VLAN 104 or 105. You have all these VLANs. Every network environment typically has, tens or hundreds of VLANs. Now, if you wanted to give virtual machines access to these VLANs, you'd have to dedicate a virtual switch with a physical NIC to each one of those networks. But by giving virtual switches support for 802.1q, otherwise known as VLAN tagging, now the virtual switch that has one dedicated physical NIC to it can have visibility and connectivity to multiple VLANs. So you have one virtual switch supported by one physical NIC. This physical NIC is connected to a port on a physical switch. Now the physical switch port is configured so it can see multiple VLANs. You can pass this visibility on to the virtual switch, which passes it on to virtual machines. Now you can have virtual machines configured to connect to VLAN 101, virtual machines configured to connect to VLAN 102, 103, 104, as many VLANs as you need. Of course, you have to abide by the maximum VLANs that ESX supports, and we're going to talk about maximums in virtual networking towards the end of the module. So how do we configure VLANs on a virtual switch? So the easiest way to do this is you have a virtual switch and you create a port group for every VLAN that you want to have connectivity to. And I'm going to show you in a few seconds here. When you create a port group, you have an entry for a VLAN ID. So you can associate the port group with a VLAN ID, VLAN 101 for example. Any virtual machine that you make member of VLAN 101 automatically gets connectivity to the physical or to the VLAN that resides on a physical switch, and thereby virtual machines and physical machines can participate in the same VLAN. Alright, so let's go into the VI client here and take a look at VLAN tagging and how it works exactly in virtual switches. Let's take the virtual switch, the first virtual switch up here. Let's click on the properties. Now we can do this in multiple ways. We can click on an existing port group, which is VM network, click on edit here, and you're going to quickly notice the VLAN ID, which is optional. Now if you had your environment configured to support VLAN tagging, which is going to require obviously configuration from your network administrator so that the port that the physical NICs are connected to is ready for VLAN tagging. But assuming that part is done, you come in here and you assign the VM network here with an ID of, let's say, 101. This is VLAN ID 101. What I suggest you do here is you match up your VLAN ID in your virtual switch with the VLAN ID that's on the physical switch. That makes it easier for management and troubleshooting. So you click on OK here. Let's add another port group, another virtual machine port group, and let's call this one terminal services. Let's say this is connected on 102. Let's click next, finish, close, and now as you can see here, you have multiple port groups on the same physical or on the same virtual switch that's serviced by these two physical NICs connecting to multiple VLANs. But what kind of properties can we configure for a virtual switch? So let's take a look. Let's go into one of the virtual switches here. Let's click on properties. Let's select the virtual switch, click on edit down here, and you're going to have several different tabs that would help you configure your virtual switch. Now check this out. This is really cool. Just imagine how hard would it be on an actual physical switch if you wanted to add ports, or if you were running out of ports and needed to increase the size. You probably couldn't. You'd have to get another physical switch and attach it and then expand that way by adding physical switches. But here in a virtual switch, if you run out of ports, all you have to do is modify a setting, come up to the number of ports here, and you could change that. You can go up to 120, 248. So let's bring this down back to the original 56 here. Now as you can see, some of the configurations that you can do to the virtual switch: security, traffic shaping, NIC teaming. So let's take a look at each one of them. Let's go into security for a second here. Alright, now the policies that you can configure here, the way they propagate is if you configure them on the virtual switch, they're going to propagate to all the ports that are part of this virtual switch. However, if you configure a policy on the virtual switch and you also configure the policy on your port group, so you have the option of doing it on the switch, but you also can do it, for example, on the port group by going to edit and you go to security. So if you configure it on both, then the port group is going to supersede what's configured on the switch. So as you can see, both the port groups and the virtual switches both have three types of layer 2 security that you can configure on each of them. Let's talk about promiscuous mode for a second. The default is reject. You can set it to accept. What is promiscuous mode? So what happens if promiscuous mode is set to accept, which is enabled? That means all the traffic that's passing through this virtual switch is going to be presented to all the virtual machines on this virtual switch. Since we're configuring this policy at this time on the virtual switch level, if we switch this to accept, that means all the traffic coming into this virtual switch will be seen by all the virtual machines. Now, you can quickly see why this is set to reject. You set this to reject so that not all the virtual machines on the virtual switch see all the traffic or all the packets, because some packets might be destined for them, other packets might be destined for other virtual machines on that virtual switch. Virtual machines do not need to see or know of the virtual of the packets that are passing through the virtual switch, but that they are destined for other VMs. Now, why would you set this to accept? Can anyone tell me? Anybody can think of a reason why you would set this to accept? Come on, there's got to be someone out there. Alright, there you go, good. Alright, the reason you would put this to accept is if you're deploying an intrusion detection system, for example, you would select accept because then you want this intrusion detection system to examine all the packets in order to find any inconsistencies or any problems that might occur. So this is one of the reasons where you would set this to accept. So MAC address changes. Now, in order to explain MAC address changes, I'm going to bring up a slide here. It's going to make it a little easier for me to explain this. Alright, so what happens here is that the MAC address that's defined in the guest operating system, as you can see in our figure, it's a Windows operating system. When the MAC address in the guest operating system does not match the MAC address specified in the VMX file. The VMX file is the virtual machines configuration file. So basically, the address in the guest operating system and in the VMX configuration file need to match before traffic can be allowed to pass through. If they don't match, then traffic is rejected. Now, MAC address changes is, as you can see because we've underlined it, is for incoming traffic into a VM. Now, for outgoing traffic from a VM, again, if the MAC address that's specified in the guest operating system does not match the MAC address specified in the VMX file, then the traffic is not going to pass through. Alright, let's go back to the VI client here. So now, what's the best, most secure way of configuring this? The ideal way is to have all three of them set to reject. This is the most secure way. However, by default, promiscuous mode is set to reject, MAC address changes is set to accept, and forged transmits is also set to accept. So now let's focus our attention a little bit on traffic shaping. So what is traffic shaping? Traffic shaping allows the administrator to control the amount of outbound bandwidth available to virtual machines that are connected to a virtual switch or to a port group. Now, traffic shaping is disabled by default, and the reason being is network adapter cards are relatively inexpensive network components nowadays, that it's less administrative hassle to add more physical NICs to allow for more bandwidth or to do NIC teaming than it is worth the time to sit here and micromanage traffic shaping. However, in environments where you need to tweak the traffic shaping or to tweak the amount of bandwidth that's available for virtual machines as far as outbound traffic is concerned, you can enable it, and by enabling it, then you have three options here to control it. So the average bandwidth is the average kilobits per second allowed access to the virtual switch over time. Now, peak bandwidth is the kilobits per second the switch can handle before it starts to drop packets. This is the peak amount, the maximum amount that it can handle before it starts to let go of packets. Now, the burst size configuration, which is in kilobytes, allows you to control what is the burst amount that you want to allow before it starts to queue up packets for later transmission. So again, by default, this thing is disabled, and unless you absolutely have to, unless there's a problem with limitations as far as expanding your environment, or if you're using certain models of blades. Nowadays, most of the blade systems allow for expansion as far as bandwidth and I/O and NICs are concerned, but in the event that you need to do traffic shaping, it is available to you in three different configuration methods. Alright, so now let's move our attention to NIC teaming. Now, as we've been talking about all along, what NIC teaming means is when you assign multiple physical network adapters to a virtual switch, you create a NIC team. And a NIC team is useful because it provides redundancy and balancing of IP connections to a virtual switch. Now, as far as load balancing is concerned, you have several different options of configuring load balancing between physical NICs when they're configured on a virtual switch, and we're going to go into each and every one of them. Let's start off by talking about route based on the originating virtual port ID. So when a virtual machine is ready to transmit its packets out to the outside world, it's going to notice that the virtual switch that it's connected to has multiple physical network adapters, and it's going to have to choose which physical network adapter to use to send out its packets. Now, when you use route based on the originating virtual port ID, this means that the virtual port that the VM is connected to, so let's say on a virtual switch, VM A is connected on port 1. Then this port 1 is the criteria that's used in the selection of which physical address or adapter is going to be used to push the packets coming from the virtual machine. So in other words, the criteria used here is the port ID where the virtual machine is connected on the virtual switch. Alright, so now the second option for load balancing here is route based on IP hash. What this means is basically the uplink is going to be chosen, so the physical adapter, the physical NIC adapter, is going to be chosen based on the source and destination IP hashing. The third option in this list is route based on source MAC hash. And what this basically means is that the uplink or the physical NIC is going to be chosen based on the MAC address of the virtual machine where the communication originated. So now the last option is use explicit failover order. Now I'll shift your attention down to this box here. So as you can see, we have two active adapters. So when this option is selected, what's going to happen is the highest number adapter is going to be used. So in this case, it's going to be vmNIC 0. vmNIC 0 continues to be used as the default adapter for transmitting data to the outside world. In the event that that becomes unavailable, then you go to the next one on the list. Alright, so let's put this option back to what it was for the default and move on to network failover detection. So you have two options here. The first one, which is the default, is link status only. What link status only means in a very basic form, if there is a network cable connected to the physical adapter, it's going to notice that there is a connection. It's going to detect a connection, and as such, it's going to report that everything is fine and dandy. If a network cable is unplugged, for example, or a connection is not detected, it's going to report a network failure. So the second option is beacon probing. Now with beacon probing, in addition to using link status, it also sends messages to the adapter, and in the event that it doesn't receive a message response back, an acknowledgement back from this adapter, it reports a network failure. Notify switches. This is a really cool setting, and your options here are yes and no. Yes is selected by default, and then you can choose no if you like to from the drop-down menu. However, this is a very useful feature. What it does is it notifies the physical switches of any changes that happen. Now, why is this important? Because in a NIC team, you have multiple physical adapters that are servicing a virtual switch. So at any given time, these physical switches need to use one or the other as far as physical adapters that are configured for the virtual switches are concerned. So it can only send traffic via one of the physical adapters. If one of the physical adapters fails and it can't use it to send traffic, then it's going to take a while without notify switches for the physical switch to understand that, okay, this adapter has failed, start routing to the other adapter. But with notify switches, anytime you add a new adapter to a NIC team, the physical switches are notified. Anytime a failover event has occurred and traffic is being sent out a different interface, physical switches are notified. And when you notify them, what they do is they update their lookup tables. By doing that, you prevent latency and slowness from happening because the physical switches are kept up to date and they know which physical adapters are available for them to send traffic to. Now the only time you want to set this option to no is if you're using Microsoft Network Load Balancing in unicast mode. This is not supported, it has a lot of problems. If you're using Microsoft Network Load Balancing in multicast mode, you're fine. You can keep this to yes. Now, for more information on this particular issue, you can revert to VMware Knowledge Base article number 1556. It explains this in greater detail. Alright, now let's focus our attention on failback. The default option for failback is yes, and you can set it to no. So let's talk about yes and no here. What failback means in this event here is it determines how a physical adapter is returned to active duty after recovering from a failure. So in the list down here we have vmnic0 and vmnic4. Let's put vmnic4 into standby mode just for the purposes of this example. So vmnic0 is functioning. It's fine. If it fails, what happens is the standby adapter is going to kick in and it's going to become the active adapter, thereby forcing vmnic0, which is not functioning at this time, to go into standby. And we're going to put this in standby to illustrate this properly here. Alright, now after vmnic0, and if vmnic0 recovers, if the option is set to yes, then what happens is vmnic0 is going to assume its active role again, and it's going to force vmnic4 into standby mode. Now if you set this to no, what happens is, in the event that vmnic0 fails, it goes into standby mode and it stays there until the active adapter fails, at which point it kicks back in and assumes active duty. Now in the list down here, it goes without saying that active adapters are the ones that are going to be in production, whereas standby adapters are adapters that are not being used at the moment and only become active when physical or active adapters are not functioning properly anymore. Unused adapters are adapters that you specify for not use, for no use. Alright, so you guys check this out. So I was trying to stop the video because I made a mistake, and as I was trying to wrap up the module, and you guys can rewind and check this out, I was getting towards the end, and when I minimized the virtual infrastructure client, there was a window that showed up, and I didn't want to show this as part of the video. Now, I seem to have locked myself out of the service console. I can't get back in to the service console. So what I'm assuming, what I'm guessing happened is somehow in the last screen where I was demonstrating, I must have switched the active adapter for the service console, for the virtual switch where the service console is connected, from vmnic0 to vmnic4, I believe. Or I must have made some kind of a change where I can no longer access the service console. So you guys check this out. So I'm going to bring up a command prompt here, and I'm going to try to ping the server. And as you can see, the request is going to time out. And if I try to access the server via the VI client, I'm also getting an error message. So what do I do? Now here's a perfect scenario where another service console with a different IP address would have been perfect, because I could have logged in to my ESX server using that backup or secondary IP address. Now at this point, what are my options? I can't use SSH, because if I could connect via the IP address, I would have been able to connect via infrastructure client. So my only option is either physical console access to the server, remote KVM, ILO, or DRAC, or some other sort of remote console access. So I've brought up the ILO for this server here, and let's go ahead and log into it. But before I do that, and while I'm trying to log in here, I want you guys to tell me, how are we going to fix this? Now we obviously have a problem with the service console. We've covered this before, and I want you guys to see if you can remember, what do we do? What am I looking for? What are we trying to check for here? Anyone? Anyone? Alright, so the first thing we're going to do is we're going to run the command esx cfg -vswitch -l. Now keep in mind, this is not a pre-planned exercise. This just happened, and we're going to troubleshoot something that just happened with me, and I'm not trying to fix it. I want to show you guys how we can get around that. So we're going to take a look here. Whoops, and the first thing you're going to notice is what? Before I say it. Alright, so the first thing you're going to notice here is that the service console, or the virtual switch configured for the service console, has two physical NICs, vmnic0 and vmnic4. Now somehow then, I must have changed either the load balancing policies, or something in that screen that's making the service console inaccessible. So how do we fix it? What commands do we issue to remove vmnic4, keep everything at vmnic0, and see if we can access the service console again? Alright, so if somebody said esxcfg -vswitch space dash capital U space vmnic4 space v capital S switch 0, then you're absolutely correct. What is this command going to do? What this command is going to do is it's going to remove vmnic4 from vswitch 0. It's going to unlock this NIC from this virtual switch. Alright, so let's take a look at the command again. Let's do esxcfg -vswitch space L. Whoops. Be nice if I could type. Let's try this again. And would you take a look at that? Now we've removed vmnic4 from the service console, from attached to the virtual switch that's attached to the service console. Now let's see if we can access the service console and if we've done any good here. Alright, let's see if we can ping this thing now. Whoa, there you go. That looks much better. Alright, let's try to log in. And I could tell that this thing is probably going to work. Come on, loading inventory. There it is. Alright, awesome. And there it is, we're back. I mean, this is a perfect example of why the service console needs multiple entries. And again, this was not a pre-planned exercise. This just happened with us, and I just let it go, and we troubleshooted something as it broke. So now let's see. I'm going to extend this video just a little longer. Let's see if we can figure out what we did here, even though we've probably removed. Well, there it is. vmnic4 is still configured because it only removed it from the configuration file, as you can see here back on the ILO. Let me scroll up here so you guys can see this a little more clearer. Alright, I guess I can't scroll back up, but it gave me an answer when I removed vmnic4 that it said it only removed it from the configuration file. Now you can rewind the video just a little bit and you'll see that. So what happens is, I guess it's still configured here in the virtual infrastructure client in the database. So let's go back into the virtual switch properties and take a look at what was going on here. Alright, now the first thing I can notice is beacon probe is selecting. I don't think this was what caused it. The failback may have caused this, but I think what happened is vmnic4 was part of the active adapters, and it was probably the first adapter on the list, and that's probably what happened. So let's give those settings their defaults. Let's go back in here. Let's go into network adapters. I'm going to remove vmnic4. Yes, I'm sure. Thank you very much. Close. Let's minimize this. And now we can finally wrap up this video. We're going to go into back to the presentation, take a look at the virtual networking maximums. Alright, so it's very important when building, designing, or architecting the environment that you know what your limitations are so you can architect properly. This slide is also particularly important for those of you that intend on sitting and taking the ESX4 or the vSphere, a VCP exam, because the exam typically tends to focus a lot on maximums in general. Now, as far as ESX4 networking maximums are concerned, what I've done here is I've created a general column, which means that column will apply to both the standard switches and the distributed switches. Now, so far in this lesson, all we focused on have been the virtual standard switches. Now the lesson that comes after this will be talking about virtual distributed switches, but I wanted to give you kind of a summary here before we wrap up this lesson about some of the networking maximums that you have with ESX4. So as far as virtual switches are concerned, you can have 248 virtual switches per host. And virtual switches, what I mean by that is virtual standard switches. This is typical virtual switches that come with ESX4 and before, or earlier versions. And then you can have up to 16 virtual distributed switches per virtual center. Now, as we'll talk about in the next lesson, virtual distributed switches are at the virtual center level, not the ESX level. Now, as far as ports, you can have up to 4,088 ports per switch. That's on the virtual standard, and on the virtual distributed you can have 6,000 ports per virtual center. So you can see that there's a significant change here. Now, as far as ports per host are concerned, you can have up to, again, 4096. Now, that means that collectively, no matter how many switches you have, if you have 10 or if you have 1, you can have more than 4098 ports per host, and the same thing goes for the virtual distributed switches. It's 4096. Now, I'll leave the rest of these on screen here for you guys to go over. It's very straightforward. The only thing I'm going to talk about here is the VM direct path per host. So if you were trying to attach a PCI card directly into a virtual machine, you can only do up to 8 per host. So after 8, you wouldn't be able to attach from one particular host PCI adapters directly into a VM. Alright folks, so this brings us to the end of this lesson. I hope it's been informative for you, and I'd like to thank you for viewing.